So in the last installment, I told you in some detail about the statement of this theorem that if you take a random curve of this sort on n vertices, then the area of the most efficient surface, oriented surface to fill it is on the order of square root of n log n. And now I want to give some rather vague ideas of how you might go about proving this theorem. And the first idea is to reduce to a lower dimensional problem by slicing. So what do I mean by slicing? Well, in this cube, I can take a square slice and look at the intersection of my curve and my surface with that slice. And so first of all, if we look at the intersection of the curve with the slice, what is that going to look like? Well, it's a bunch of points, but more than that, the curve has a directionality to it, right? So sometimes it's going down through the slice and sometimes it's going up through the slice. So I'm going to draw those intersections in different colors. So the ups are going to be in green and the downs are going to be in red. And so what we get is that a curve, when you take a slice of it, becomes a bunch of red and green points. Or if you want, you can also think of those as negative and positive points. And then what happens to the surface, right? It also has an intersection with the square, and that intersection is going to look like a bunch of curves that connect the red and green points to each other. And here's, why does it always connect red points to green points? Well, this is a consequence of us taking an oriented surface. So a surface gives you a matching between the red and green points. And so, this allows us to translate the filling area into another language, because if we take the area of a surface, probably in your calculus classes, you computed some areas of things, and you can compute them by integrating lengths of segments, and you can do the same thing here. And the area of the surface is going to be the integral from 0 to 1, as you take different slices of the total length of the curves in the matching. And so, if we want to take the area of the most efficient surface, so the area of the optimal filling surface, well, you don't know that the slices of that filling surface are actually going to be optimal matchings, but they're going to be some sort of matchings. And so this is going to be at least greater than or equal to if you integrate the total lengths of the optimal matchings. And in fact, this inequality, the two sides in this inequality are not that hard apart. Sorry, not that far apart. And so this is kind of a hard fact that they're actually close to each other. So they only differ up to a multiplicative constant. So the other, right, the other direction of the inequality you can get if you just put a constant in front of one of the sides. Okay, so now we can switch to thinking about these matchings. And the nice thing for me is that the people have thought about them before me. So this rest of what I'm going to be talking about is actually due to some Hungarian mathematicians, Ajtai, Komlos, and Tusnadi, who studied this in the 1980s. So not that long ago, it's not that old. And so the second idea is instead of measuring, right, so now we're thinking about random matching. So a bunch of random red points and a bunch of random green points, and can we match the red points to the green points? And so it turns out that if we want to bound the size of this matching, we can think about matching our random points to a uniform grid, because then to move the red points to the green points, we can just move, well, we can move the red points to the uniform grid and then to the green points. Right, and so that, right, both of these steps are like this. So that means that the total movement that you do is going to be greater than or equal to the length of whatever the optimal matching is, right? So whatever this process is, this actually gives us an explicit matching. And so it's certainly an upper bound for the size of the optimal one. So how do we move random points to a grid? So step one, we have a bunch of random points, and I'm gonna draw a line down the middle, right? And so law of large numbers, to the right and left sides of the middle, you don't have exactly half the points, but you have around half the points. And you can draw another line over here on one side or the other, we don't know, where exactly half the points are on the other side. Right, and so then the way we start, so our ultimate goal is to split up the square into lots of tiny boxes with each point sitting in its own box. And so the first step to do that is to sort of move this line to exactly halfway and drag the points along. So we drag the points along as if they were drawn on the sheet of saran wrap. And so we're stretching the sheet of saran wrap on this side and sort of compressing it on this side. And now there are equal numbers on each half. And this is a fact that I'm not going to explain to you. It turns out that the distance between these two lines is going to, on average, be around 1 over root n. So for any given toss, for any given set of random points, it might be smaller or bigger, but on average, it's going to be about 1 over root n. And this is going to be actually the same on every step. So that's sort of the key observation here. Right, step 2, we've already split things down the middle this way. And now we want to split them down the middle this way. And so maybe here we have more points on the top. And so we drag them down. Here we have more points on the bottom. We drag them up. And this dragging distance is still, on average, 1 over root n. And right, keep going like this. So step 3, right, we maybe have to drag this side this much, this side this much, and again, it's about 1 over root n. And so, right, as we do this, we keep splitting things up. So it takes about log n steps to get each point in its own box. And each step each point moves by about 1 over root n. And the directions end up being random, right? It might move left one step and right the other step. And so most of them will cancel out. So what does this tell us? Right, the expected total distance that the points will move, right? Well, that's going to be the number of points times how far they move. So times 1 over root n, this is the movement per step. And times square root of log n, which turns out is the number of steps usually that won't cancel out. Right, so if you flip a coin n times and you go left when you get heads and right when you get tails, then usually after those n times, you end up about square root of n. Sorry, I should be saying k times and square root of k. You end up square root of k away, right? And k in this case is log n. So we're square root of log n away. And so, right, this gives us our square root of n log n. So, right now we have these inequalities. We know that the length of an optimal matching is at most square root of n log n. We also know that the integral of those optimal matchings is at most the area of the optimal filling surface. So actually together, these two inequalities don't tell us anything. So we actually need the two inequalities in the other direction, and then we get this approximate equality. And so that seems hard, right? So in order to get an upper bound on the length of an optimal matching, we just had to find a matching, right? But how do we say, okay, no matching can be better than whatever? That seems hard. And so it turns out what you want to do is to use the fundamental theorem of calculus. So someone gives you a bunch of red and green points, and what you can try to do is build a function from the square to the reals. So you can think of this function as giving you a mountainous landscape, right? The height, it's a height function. Right, you do this based on the red and green points, or positive and negative points, whatever, right? So you build a function so that its gradient is, I guess, the norm of its gradient, the length of its gradient. So basically its slope is at most 1 everywhere. So the slope of this mountainous landscape is not too big. And if you take the sum of all the red points, sorry, the sum of f of x, where x is all the red points, and you subtract the sum of f of x, where x is all the green points, you get at least our favorite number, square root of n log n. So what is this saying, right? It's saying the slope is not too big. And it's saying that the red points are mostly concentrated on the hills, and the green points are mostly concentrated in the valleys, so that, right, you know that since the slope is not too big, the distance from a hill to a valley is kind of far away. And so that means that in order to connect all the red points to all the green points, you have to go kind of far, right? And this is a sum, so it's not like all the red points are on the mountain peaks, but at least like more of the red points are on the mountain peaks than in the valleys, and vice versa for the green points. And then, right, so how do we turn this intuition into math, right? Then the total length of a matching, well, you can think of it as you take the function just 1 and you integrate it over all the segments, all the line segments of the matching, right? And that's going to be greater than or equal to the integral over all these segments of the gradient of f, and that's greater than or equal to the integral over all the segments of the directional derivative of f in that direction, right? And that, by the fundamental theorem of calculus, is greater than or equal to this thing here. So that's how you get the other direction, except now you actually have to build this function, and that's maybe the trickiest part of the proof. And of course, it's not going to work always, because you could choose a bad matching where it doesn't work, but you have to prove that it works almost all the time. And similar sorts of ideas go, so this is the idea for the inequality opposite this. And for the inequality opposite this, there's a similar idea that you can apply. So that's all the math I want to talk about. I hope you enjoyed it.